problem. Now, we see a lot of that test terminology bleeding into our program specification already. Test this, test that, test initial. What our spec will do is keep the same structure, but change the terminology, and it will look like this. You create a context called a new bowling scorer. And you give it a block, and within that block, you still have a setup section, and that creates the environment for the context. And then you have a bunch of specifications that come after that. In this context, then, a new bowling scorer should have a 0 score, and we assert that at score should be 0. Notice how it reads very nicely. It reads like a specification would. Not only do the strings that we use here and here make it read better, but the very fact that the scorer should be 0 reads very naturally in English, which is kind of a nice thing. Truthfully, this is merely a change in terminology. We're not changing the basic way that we're doing testing, but what it does, it focuses you on the fact that here's this context, we set up for the contexts, and then we have a bunch of specifications. Now what I've found, when I start thinking in this way, my tests become a lot smaller and more focused. And it really changes the way that my tests begin to get structured. Okay. Notice too that if we focus on the strings given in the example, we can take those, create an outline from them, and when we complete the entire spec, we would have something that might look a little bit like this. And in fact, our spec will take your specifications, create an HTML file that will look like this, and you can give it off to people and say, this is my specification piece of my program. It reads very nicely like a specification. Okay. It moves us away from thoughts of verification and more towards the thoughts of design and specification. Questions at this point?
Just have a quick question, which is that in the case of like test unit and stuff, even though Ruby's new, there's still enough information to find on the web. What can I find? You know, if I go out and search for our spec, what am I going to see? Mainly just because, you know, I might choose a tool that may be a little harder to use or less what I need, just because there's a volume of information and a lot of guidance.
Right. Our spec is very new, and it's still under development, and they're still deciding some architectural issues. So I'm not saying everybody go off and use our spec right now. I am saying, hey, this idea of thinking about specification rather than testing is a good thing. And whether you continue to use test unit or JUnit if you're Java programmers, you know, if you mentally start adopting the idea of specifications, it'll change the way you do your tests, whether you actually use this library or not. But the library got me thinking, what is a common objection that people have about using tests, or in this case, our specifications, for a specification?
A user doesn't understand them. It's not a word.
Not a word document. Yes, I have run into that too.
It's too close to the implementation.
Close to the implementation? One of the things that I have heard is that tests are not specifications, that you cannot specify things using tests. And actually what they're doing is something called specification by example. Let's talk about that for a minute. When I was here last year at OSCON, I don't know if you can see that very clearly. I just got my digital camera and I didn't know how to work it yet, so the picture's very fuzzy. But if you look, you can see here, there's a couple triangles here on the floor and a couple marbles and things laying around. There was a bunch of people sitting in a circle right outside here, and they all had these triangles and marbles that they were playing with. And what would happen is that one guy was the master, and he would lay down a set of triangles on the ground, and the next guy, in a particular pattern, the next guy would lay his triangles down in a particular pattern, and the master would tell the student whether that particular pattern, his particular pattern, had the Buddha nature or not. If it had the Buddha nature, he would get a stone. If it didn't, he wouldn't get a stone. And everybody would go around the circle, laying out example patterns of triangles. And the goal was to determine the rules for the pattern. What were the rules for having Buddha nature in that particular term? So let's look at this a little bit. One of the triangles we saw were 3 triangles of different colors laying flat on the ground. Another one was 2 blue triangles upright, and a green triangle laying down. And from the picture, I thought it was a rectangle. Someone else later told me that they're all triangles. So this is a triangle with its base facing towards us. Another one was just a red and yellow triangle sitting upright. And they all had the little stones. That all meant they had the Buddha nature. So, given these 3 patterns, what are the rules for putting those triangles in that pattern? What is the rule for Buddha nature?
They all understand one.
At least one up, except the first one, they were all laying flat.
All laying flat.
Yeah, it's hard to see on the 2D thing. Yeah.
Symmetry. Symmetry.
Symmetry? Symmetry, okay.
They'll have at least one triangle or 2.
At least 2. Yeah, there's a couple, and I thought maybe, I'm not sure what the rules for this particular game was. Maybe it was at least 2 upright triangles. Maybe the rules were you need an even number of upright triangles. Problem is we don't have counterexamples. And if you were playing the game, you would lay out, if you thought you knew what the rules are, you might set up an odd number of triangles to see if that had the Buddha nature or not. And you would eliminate possibilities and narrow down on what the rules were. What we see here is an example of specification by example and counterexample. We're specifying the Buddha nature through a set of examples of triangles. Let's look at another situation. Number sequence. What's the next number in the sequence? 13? Who said that? Why? Increment by 2, or we could say they're all odd numbers. It's another way of saying that. Okay, and at the top we have an example of the sequence. We can also specify it with a little pseudo Ruby. Even doesn't exist in the Ruby library, but we could easily write it and add it to Ruby. And we can say not even, and that is the rule for including a number into this sequence. How about this sequence? Also 13, yes. But what's the rule for this? Prime numbers. These are all prime numbers. And if we wrote a Ruby function called factors that would return a list of all the factors of a number, if the size of that list returned by factors is 1, then that would be a prime number. So we can specify it through another formula. How about this one? This is tougher. When I first gave this talk at the Columbus Ruby Brigade, I put this example up, and someone almost immediately called out, 4!
25.
No, it's 4.
Oh, it's 4?
It is 4. And I said, how did you know it was 4? They said, well, I went to the online encyclopedia of numerical sequences and typed in the numbers, and it said 4. This is a sequence, and the rule is, if you take a number in the sequence, and if the number is even, then you divide the number by 2. So in this sequence, 10 is even, so the next number is 5. If the number is odd, such as 3, then you multiply that number by 3 and add 1. So 3 multiplied by 3 is 9 plus 1 is 10. 10 divided by 2 is 5. 5 tripled is 15 plus 1 is 16. Then 16, 8, 4, 2, and 1. And if the sequence terminates in a 1, and that's what you don't go any farther than 1, then that number you started with, and indeed all the numbers in that sequence, are called wondrous numbers. Why is that important? Well, the question is, do there exist any numbers that are not wondrous? In other words, do all sequences eventually terminate in 1? Well, pi, okay. Integers. Begin with an integer. No one knows. That's, at least at the time I learned about wondrous numbers, that was one of the unknown mysteries of mathematics. And I don't know if they've solved it in the years since I first learned about it or not. But again, we see an example of specification by example and specification by formula, kind of a more formal way of specifying things. Turns out humans are pretty good at doing the specification by example thing. We can take a series of examples and extrapolate from that to the general. Are really good at doing that. Computers not so good. Some things are tougher, even for us to figure out. But we are very good at finding patterns in things. So let's think about specification. Is there another way to specify the behavior of a program other than through the example way that Unit and RSpec both do? Well, by contract, and this is something I picked up from my case. How many people have done design by contract? A little bit. So it's good to cover what a contract is. A contract is an agreement between two parties, a client and a supplier. For example, I'm having a lawn party tonight. I need my lawn mowed. So I would say to my son, Dan, I need my lawn mowed tonight by 5 o'clock so I can have my lawn party. And Dan, being the good son that he is, says, sure, Dad, no problem. You need to fill up the gas mower, or the mower with gas before I can mow it. So he agreed to put some conditions on that. That is a contract between us. There are two parts to the contract. There is a precondition. The mower has to have gas in it before he will mow the lawn. The second part is the post-condition, and that is the lawn mowed by 5 o'clock tonight. Now, what's nice about design by contract is that it gives both parties involved in this interaction very clear responsibilities on what they're supposed to do. The precondition is to make sure the lawnmower is filled with gas. If I don't fill up the lawnmower with gas, can I expect the lawn to be mowed?
No.
Really? Dan is a really good kid, and he might go out and fill up the mower himself, or he might go out with scissors and cut it, but I don't think it can be done by fire. He might mow it, but he might not. It is not, the contract does not bind him to finishing the lawn by 5 o'clock. I do not fulfill my part of filling it up. Post-condition is his responsibility. Assuming that I do keep a condition, he must make sure the post-condition is fulfilled and have that lawn mowed. Benefits like that are clear in a contract. Obviously, the benefit is that I get the lawn mowed. The benefit to Dan is a little surprising, but he gets the benefit of the precondition. He does not have to go out and buy gas. So the precondition is a benefit to the supplier. Questions? Now we can talk about contracts in a software context as well. And here we get to this example, right? We have a main program, we have a stack. And there's a between them. The main program says, hey, I need the item in that stack right there. The stack says, no problem. I can give you that top item, assuming that I have any items in me at all. If I'm empty, I can't give you it. So again, we have a precondition, not empty, and a post-condition, the value returned was the former top item of the stack. So it turns out we specify program behavior through the idea of contracts. Okay. Let's go into example a little bit farther. There are two kinds of methods to write an object. The first kinds of methods are called queries. If you look at a stack object, some queries might be what is the depth of the stack? In other words, how many items are in it? What is the stack currently empty? And what is the top item in the stack? About queries is that they do not modify the state of the object. So you can send, ask the empty question as you want to, and the stack does not change. The other kind of methods you write are command methods. They change the state of the. Now in Eiffel, you generally did not return values considered a no-no. In Ruby, everything returns a value, so you can't really do that pure separation that Eiffel provides, but we tend to ignore the value commands for the most part. So, I was thinking, when I first heard about RSpec, I got thinking that you can do specification in such a way that kind of red-green refactor feeling that you get in development, right? Because generally in Eiffel, when I was doing Eiffel, what you would do, you would sit down, and you would think really, really hard about the stack. And you would think of all the methods that you have, all the contracts that you had. And then once you had, it'd be like an interface in Java, except that it had contracts attached to every method. So now you have the calling signature and the parameter path each method. But you also had the semantics of it defined in your interface. It was a really true interface with behavior specification. That was all done up front, big up front design. And I really like the red-green refactor approach of test-driven design. Is there a way to do that in Ruby that you kind of get that feel? The rest of this talk, we're going to look at a really small framework that I kind of threw together these ideas. Now, it's not ready for publication. The gem. If you grab the presentation from my website, you'll have all the code, but it's not really a production-ready thing. It's kind of an experiment I thought I would share with you. So, you start off with everything empty. Just three parts to this framework when you write a contract. You start off with a specification, a PC or designed by contract specification, and this is certainly empty, but it's a specification for stack. You'll have a class stack, and then you have a piece down here that connects the class with that specification. Now in Eiffel, you put the contract into the class that you're doing. Actually in Eiffel, interface, and we don't have interfaces in Ruby. So I connect them separately out. And what makes the interesting thing about this, it makes it possible for me to write a stack that conforms to the stack specification. Your version of stack, maybe you'll write a stack, and you would write a linked list stack, and I'm using something else. So multiple implementations can all be checked against the stack class. So, let's see what would happen if we do the red-green refactor process here. So we start and we run the Ruby. We get validating my stack against stack, and everything's green here, everything's happy, no problem. And which makes sense. I mean, if we look at it, there's no specifications and there's no code. So we have no behavior matching no specification. That makes sense. So we add our first contract. And we're going to start with the method. The contract looks like this. You give it the name of the method that you're specifying the contract for, and inside the block, you specify your pre and post condition. Just one post condition for the string here, right, is empty if depth is 0. That is the post condition, and we do that so that error messages which post condition failed. That you give to the post condition has an argument result, and that is the value returned from empty. We can make assertions about the return value. Now, a simple assertion is that the result of empty is going to be the same as the comparison of depth against 0. So we have a query, and when it's 0, the stack is empty, and that is the behavior of empty. So, let's run it. And we still get green. What happened? Why didn't the contract fail? Well, the reason it didn't fail is that you need some code to actually create a stack and tell it. And this is something that you don't do in Eiffel because they assume contracts in your production code, or at least during your development cycles, you're going to be running it against the real thing. We want to run it in a more testing environment. So we're going to create an example section of our specification. And in the example, much like the contexts of RSpec, perhaps, It's called initial condition, and then we'll get the stack object. Notice it never creates the object under attack. That's always handled by the framework, so we can test against different kinds of classes. So it passes in the stack, and we just ask, is the stack empty? We just exercise that code. And if we run that, yes, we get a horrible error message. Like I say, this is just prototype code. But the key is, in here we see an undefined method empty appear as a violation, as a problem. Now that's okay. I really don't like the fact that I have the stack empty in my initial conditions. Does that mean I'm going to have to list all the methods in there and try them all out in my example? I'm not sure I like that. There's another way of specifying behavior in a contract. Other than preconditions and postconditions, there's something called an invariant. So let's take our empty method, and the contract for empty now just states that it's a query. That's just a hint to the framework that it doesn't modify the stack. The invariant section here says that empty is equal to depth of 0. And invariants are true all the time. So that means our framework can check for invariants every single step of the way, every time an object is accessed or created or you do anything with an object. We can check invariants for it. So we capture the relationship of empty and depth in this invariant. And we run it again, and we still get the undefined method empty. So it's still catching that. And I like the invariant idea a little bit better. Run with that. Now we are in the green phase where we fix up the code. We add an empty method, and we're going to do the dumb thing here. You know, you write just enough code to make your tests pass. In this case, our specification pass. And so I'm going to take it in tiny steps so we see the red-green refactor. And in real life, you take larger steps in that, and that's okay. We run it again, and we say, oops, undefined local variable or method named depth. And that is because if you look at the invariant back here, we reference depth. So we have to define depth as well. So that's the next step. Add a depth method, and just a 0, because that's all we need to make our test pass. We run it, and it says everything's happy, everything's good. Red, green, refactor, next phase. Red again, okay. We have the invariant. Now let's add a contract for push. Let's get push next. Its post condition is called stack size to increase. When I call push on a stack, one of the things that should be true after push is done is the size of the stack is 1 larger than what it was before. So we capture that like this. Depth is equal to DBC old. DBC old is a framework method that goes and grabs the old value of depth, the value of depth before push was run. So it remembers that, pulls it out, we add 1 to it, and that should be equal to the current value of depth after push is done. Remember depth up there, that line is just a piece of information for the framework, so it knows to store that off and save it for later use. It'd be nice if we could remove that, and that might be a nice enhancement to the framework. We add an example, because we need some code to exercise push now. Since this is a post condition on push, we actually need to call push to make sure it happens. And we run the specification. We see undefined method push. That makes sense. Add the push thing, run it again. Post condition failed. Good. Good, we're seeing that. Okay, so now we've got to go back in and fix the post condition. It's got to increase the depth. So the simplest thing I'm going to do is just increase the depth by 1. And I have to record depth and make it a variable now. So depth is now an accessor rather than a function that returns 0. We run it again. What I thought was simple enough to pass the test isn't. But depth and empty are tied together in a special relationship in that invariant. And our specification framework caught that and is complaining about it now. So what we have to do, there's the invariant. So what we have to actually do is go in and modify empty so it actually senses the true depth. Run it, and now our examples work again. Now, let's see, what are we doing on time here? About 10 more minutes, I think. So we're going to go through the rest of this really quickly. It's just more and more of the same. We had a post condition for push that says after you push, the top item of the stack needs to be whatever you pushed on the stack. We run it. We didn't define a top, so we define a top. We run it again. Post condition is failing. The one that we just added is now failing, so we go in and now we have to actually write some real code to push items on the stack. And we use an array. Depth is now just the size of the array. Top is just the last item in the array, and push just adds items to the end of the array. And we run that, and yes, our specification is happy again. Red, green, refactor, red, green, refactor, red, green, refactor. So you can do that using a design by contract approach to specifying program behavior, which I found very fascinating. I really like that. I'm not going to walk through POP, but we'll just point out the contract for it. It has some interesting features. It has a precondition. Now, it's interesting. We did put a precondition on push. Should we have put one on push? Perhaps. It depends. Depends on what kind of stack you're writing. If you have a stack that can grow unlimited, there's no inherent limit to the size it can grow to, there's no precondition on push. If you have a stack that has a fixed number of slots in it, and once you hit that maximum number of slots, there is a precondition on push, and that will be not full. You cannot push if the stack is full. So whether or not you put a precondition on push determines what kind of stack you intend to write. Now that's important because as you're writing client code, the client needs to know whether the stack is unlimited or not. If it's not unlimited, he's going to have to check for fullness or expect to handle an exception if he pushes too many items on it. So the contracts determine the behavior of both the client and the supplier. And it's a good way of specifying that interaction. Here's our POP condition. The stack is not empty, simple empty condition. Post condition is very similar to the post condition on rather than larger. What is, here we run the whole thing, we see that it works. What's missing from POP's specification?
Empty condition.
Empty condition?
Show it visible. That you got backed up, but it didn't last.
Right.
Right. Well,
I did it.
It should be turned off.
it should be, well,
Turns off, and then the post condition.
yeah, if it returns a value, it should return top. We could add that. But more importantly, after POP is done, what is the new value of top? How would you write a post condition for that?
That it's not equal to old now.
Well, the old top is gone, so you can't compare against the old top. What you really want to compare against is the old second from top. But we don't have a way of accessing the second of top, so there's no way to refer to it in our contract. Now, we could add that to our specification and say the post condition is that the new top is equal to the value of the old second to top. But once we do that, then we need to start specifying what the value of second to top is before and after each of these operations. And to do that, you need a third from top, and so on and so forth. In fact, to specify full stack-like behavior, you need to implement in the pre and post conditions essentially a stack to keep track of the old and new values, which seems to be a little pointless. The specification should be somewhat easier than the implementation, one would suspect. So it turns out that design by contract is really good at capturing certain things, and other things is very difficult to capture. Difference, if we went with this specification, and gave it a queue rather than a stack, it would actually pass the specifications because we don't say what new top becomes. That's okay. You can fix that by putting some inserts into the examples and capture it that way. It turns out that test-driven, if our unit and those kinds of things, test unit, very careful, it's very easy to specify that because you know what you pushed in your test, so you can check against it as you pop things off. It's an example-based specification. Here, your specifications are general. They are true all the time. Not true just in your test case, but true all the time. I saw a question back here.
Yeah, I'm back thinking still about that. Remember depth, does that imply that they're using the same object for every one of your depths?
No, the remembering is only done immediately prior to the call of the, in this case, pop method. So no, the same object is not used throughout all the tests.
This is really just a fancy way of assigning depth to a temporary.
Yeah, the way of capturing it, it's like a wraparound. Yeah. Okay. Other questions at this point? Got about 4 minutes. Yes?
Have you thought of, I mean, these contracts are all method-based, so do you think it would be, do you think it would be helpful at some point to be able to, group those and just have your spec be on the object? Or you refer to methods obviously inside.
Well, remember the contract is for each method, but the whole thing is put together in a specification that refers to the behavior of an entire object.
And that's a list of contracts.
Yeah. A list of contracts for each method in that. The nice thing is that you could write a specification for stack-like behavior and a specification for serializable behavior and say that, hey, my stack supports a contract for serializable for this, that, and that. So you can have one class support multiple different contracts covering all the behavior that you want to capture. Yeah, but the whole contract is for that entire object.
And would you recommend a kind of combined set of testing where you're doing this, design by contract and doing example-based testing?
I still like example-based testing. I think it's actually easier to write the examples than to think of contracts. But when I think of contracts, I tend to think holistically of how the object interacts with its environment. And I really like the mindset it puts on you. So I guess my goal for this talk is not to convince people all of a sudden to start using this framework. Obviously, it's just a prototype. But it's to expose you to the ideas of contracts and how contracts really work. What's nice about contracts is that it's a great way to think about the behavior of an object, particularly in something like Ruby, which uses duck typing. Right? You can pass any object in as an argument, and if it does the right thing, it will work. Well, what does the right thing mean? Does the right thing means it supports the contract that the object expects it to conform to. So, duck typing and design by contract and another thing called the Liskov substitution principle, which we haven't really talked about here, is all about duck typing. They all work together, and it's a way of making sure duck typing works. If you follow the contract idea, your duck types work properly. If something expects stack-like behavior and you implement something with the contract of the stack, it should work. We can do red-green refactor type development with design by contract. It doesn't mean you have to do everything up front. And there is some mixing of contracts and some ad hoc insertions. Probably is a good mix. Questions before we close?
Is this talk going to be online?
Yes, if you go to my website, One Step Back, that's one word, onestepback.org, and there's a sidebar with articles and presentations. You can download the PDF for this. Okay. Thank you very much. You all have a good day.